Bismillahirrahmanirrahim. Assalamu alaikum. Welcome back to our FDTD series. I am Dr. Ahsan Illahi, Associate Professor of Physics at Kamsat University, Islamabad. And today we are starting lecture 2 of this journey into computational electromagnetics. In the previous lecture, we built the foundation. We talked about finite differences, Taylor expansions, and how FDTD works in the time domain. Today we are moving one step forward. This is very important lecture because the moment we enter 2D FDTD, we are entering the real world of simulations, where electromagnetic waves actually spread out in space, interact with boundaries, reflect, bend, and do all sorts of beautiful things. Whether you want to simulate antennas, waveguides, microwave circuits, optical devices, or even photonic crystals, almost everything starts from this 2D formulation. And of course, we will also meet the legendary E cell introduced in 1966, the heart and soul of FDTD. Don't worry, we will go slowly, step by step, just like we did in lecture 1. So let's begin. Bismillah. So now let's begin the real technical part of lecture 2. Up to this point in the course, we have talked about the idea of finite differences, how derivatives can be approximated, and how FDTD works in the time domain. But we notice something important. We never actually built a full 1D FDTD formulation. And there is a reason for that. In real electromagnetics, very few problems are generally one-dimensional. Waves don't move only along the straight line. They spread, bend, scattered, and interact in areas and volumes. So instead of spending time constructing a complete 1D version and then rebuilding everything again for 2D, we directly start with 2D FDTD because this is where practical engineering and physics simulations actually begin. Most real-world EM problems are either in 2D or three-dimensional. So jumping straight in 2D will prepare you almost every shape of simulation you will ever perform. Now, even in 2D, electromagnetic fields can behave in two different modes depending on how the fields are oriented. These modes are called polarization. TE or transverse electric, the electric field is perpendicular to the direction of wave propagation. TM, transverse magnetic, the magnetic field is perpendicular to the direction of propagation. These two polarizations are not just theory, they are extremely practical. In fact, any real electromagnetic simulations can be expressed as a combination of TE and TM modes. If you master these two modes in 2D, you can model almost any wave behavior. In this lecture, we will start with TE polarization, derive its Maxwell equations, and then construct the famous Yee cell for the 2D case. Let's move ahead. TE polarization components. Now let's take a closer look at the field components involved in 2D FDTD. When we talk about the electromagnetic waves in 2D, fields can be arranged in two different polarization, TE and TM, depending on which component are zero and which are non-zero. Let's start with TE mode, which stands for transverse electric. In TE mode, the electric field is transverse, meaning that it does not have a component along the out of the page direction. So the non-zero field in TE mode are Ex, Ey, and Hz. You can think of this as the electric field lies in the plane and the magnetic field pops up out of the plane. So let's contrast this with TM mode or transverse magnetic. In TM mode, the magnetic field is transverse, meaning that the magnetic field has no Hz component. The non-zero component for TM mode become Hx, Hy, and Ez. So here the simulation flips. The magnetic field lies in the plane and electric field pops out of the plane. These are the two fundamental ways electromagnetic waves can exist in the 2D environment. For today's lecture, to keep things clear and focused, we will work only with TE polarization, meaning we will track Ex, Ey, and Hz across the grid. Understanding these components clearly, we will make the next steps deriving Maxwell equations, building the Yee cell much easier. Now we will derive TE mode Maxwell equations step by step, slowly and clearly. We start from the two curl equations. Del cross H is equal to epsilon partial E by partial T. Del cross E is equal to minus mu partial H by partial T. These are the backbone of electromagnetic wave behavior. To compute a curl, we use a very beautiful tool, the determinant form. This determinant is like a machine. It takes the component of a vector field and automatically produces the rotation of that field. Once we expand this determinant, we get the exact component-wise curl formula. This will be the foundation for both TE and TM mode derivations. So curl of H in TE mode. In TE mode, the magnetic field has only one non-zero component Hz. The electric field has only the X and Y components. We plug these into the curl determinant of H. When we expand this determinant, the two components fall away because Hx and Hy are 0. This leads us with a very simple vector partial Hz by partial Y minus partial Hz by partial X, 0. Maxwell equation relates this curl directly to the time derivatives of Ex and Ey. When we match the component, we get the first two TE equations. These equations tells us that the changes in magnetic field create the electric field, and exactly how they do so in 2D. Curl of E and final TE equations. Now we compute curl of electric field. Again, we write the determinant, but this time, because we are in 2D, all partial by partial z terms disappear. This makes the x and y component of the curl 0. The only survival is the z component, partial Ey by partial x minus partial Ex by partial y. Maxwell second curl operation says this must equal to minus mu partial h by partial t. Matching these gives us the first, matching these gives us the third TE equation, which is partial Ey by partial x minus partial Ex by partial y is equal to minus mu partial Hz by partial t. Putting all three together, we get the complete set of TE. We get the complete TE set. These equations are what the FDTD method will discretize on the G grid. This is the heart of 2D FDTD. Thank you.